Recording. Hate doing this. Okay. So we are going to be looking at limits at infinity still, but of absolute value and radical functions. We're going to be looking at them through the lens of the rational function, so we can still use that limits at infinity of rational functions theorem. But when we are looking at absolute value functions and radical functions being a part of that fraction, we have to do a little extra work and a little extra thinking. So to kind of just make sure that we have some of our algebra ideas solid and set, can anyone think about a way that we can rewrite square root of AB? Joe? Go ahead, Alex. Yes, square root of A times square root of B. As long as those things are being multiplied together or technically divided, you can go ahead and separate them into their own radicals. If there's any addition or subtraction, sorry, no can do. I had the square root of A squared. Anyone have a guess as to what that would behave like? Okay, double check it. Go ahead and graph square root of A squared in your calculator. Or I guess square root of X squared in your calculator. Yeah, it looks like the absolute value graph. Whereas, what does the plain X graph look like? Yeah, just a straight line. So this part should dip down. So it doesn't just behave like a normal A, it behaves like the absolute value of A. Can anyone tell me why they think that might happen? Because of what? And what part is kind of making it so that we don't have any negatives? Yeah, the squared. So because we have something on the inside making it so that all the numbers that we're going to square root positive, that's why we have the absolute value happening when we simplify. So essentially, if that inside is making all the values positive, we're probably going to have some sort of absolute value situation when things cancel out. Does that make sense? Does anyone remember the piecewise definition of the absolute value function? No. Yep. Perfect. So it behaves like just a regular A if all of your values are positive or 0. And it'll behave like negative A if you have negative values. If you think about it, if I have a -5 here, that would go with that second subfunction, right? So it'd have -5, which is positive 5. So the reason that we're going over this is because when we're taking limits at positive infinity, things should just go straight forward as planned. But when you're taking the limits at negative infinity, if whatever function you have behaves like the absolute value of A, we have to use the piecewise definition of that function. So with that being said, let's go ahead and start off with example 1. It says determine the end behavior of this function. When I want to determine the end behavior, what do I look at? Perfect. Limits at positive and negative infinity. So let's go ahead and write up our positive infinity. All right, so how is our absolute value of X going to behave? Is it going to behave like a regular X or a negative X? And how do you know? Yeah, it'll behave like a regular X. Why? Yeah, our X values that we're approaching are greater than 0. So I'm going to say since x approaches infinity, which is greater than 0. Absolute value of x behaves like just a regular old x. So we can go ahead and replace that in this function. So the limit of that function is going to be the same limit as the function x plus 2 over 4x plus 3. It's not that the functions are the same, it's that the limits of those functions are going to be the same. How do I evaluate that limit? Yeah, look at those leading terms, which are what? Yep, x and 4x. So technically we just used limits at infinity of rational functions. Now I'm going to tell you guys right now, you do not need to write these explanations in your homework. That's ridiculous. But write them in your notes. When you guys come back to or when you start your homework later, whether that's today or tomorrow, you are going to want to know why you did certain things. Write these little notes down here. You don't need to do them again when you actually do the work problems on your own. All right, reduce that for me. What do we get? What was that? Yeah, 1/4. And the limit of 1/4 is just 1/4. So what does that mean for our end behavior? Yes. We have a horizontal asymptote there. So I'm going to write horizontal asymptote at y equals 1/4. Then you can either say as x approaches infinity, or what side of the graph is that? The right side. Okay, I want you guys to go ahead and attempt the negative infinity limit. If things go wrong, that's okay. We have erasers, and then we also have the other side of your pencil. All right, so we have the absolute value of x. Is that going to behave like normal x or negative x? Shocker, right? And why does it behave like negative x? Yes, which is less than 0. Okay, so we can use that, and we could use the limits at infinity of rational functions theorem right off the bat if you guys want to kind of quicken the work up. If you want to show every single step, that's fine as well. So if that behaves like negative x, what are my leading terms? Negative x and 4x. Simplifies the same as last time. So what's our limit actually going to equal? Perfect, negative 1/4. What does that mean for our end behavior? Perfect. Horizontal asymptote at y equals negative 1/4 on the left. Okay. Any questions here? Flip it. Again, it's wanting us to determine that end behavior. So we're going to take our limits at positive and negative infinity. So we kind of have two options for how we can deal with this. We could Do you guys see how we have a term and we have a root being subtracted? What could that signify to you? Yeah, so you could multiply by the conjugate if you want, and we wouldn't have to deal with the root in the numerator at all. But regardless, if things don't simplify nicely, which they might or they might not, but if they don't simplify nicely, we still have a root in there regardless, and I want to know how to deal with that. It just would happen to be in the denominator instead. So I want to deal with it in this form right now, just assuming things don't simplify nicely, because they don't always. So our other option is to look at our leading terms. What's our leading term in the denominator? That's super easy. Yes, 8x squared. Okay. For the numerator, I want to talk about all the powers that we see before we ultimately decide on the leading term. What's the degree of this first term right here? Second term, if you were to kind of just view that as its own term inside that root. But it's the square root of that. So like I'm saying, if we were ignoring the fact that there's a 4 there. Yeah, that would reduce to an x to the power of 1. So those both have the same degree, right? Technically, if we look at the 4, what's the power on the x that we don't see? 0. So that's not going to play any role in our leading term, right? Would you guys agree that we technically kind of have 2 leading terms here? Since we have 2 terms that have degree 1 when they're simplified. So we have 2x for sure. We just have to decide how this square root of 9x is square root of 9x squared is going to behave. Square root of 9, super simple. That's just a 3, right? But what does that x squared do to all my numbers? Makes them positive. So when we square root them, they're all still going to be positive. So is this going to behave? It's going to behave like the absolute value function because that made it all positive. But is this going to behave like a regular 3x or a negative 3x? All right, yeah, we're gonna go with the positive one because yes, we're approaching positive infinity for our x values. That is what makes the difference, is what kind of x values are you trying to plug in. So that'll just become a 3x. Combine like terms, simplify, and report back with what you think that the limit is. And you can also start off the limit as x approaches negative infinity. All right, combine the like terms. What do you guys get? (2x minus 3x). What is that? Negative x. Negative x divided by 8x squared.
Negative 1 over 8x.
Perfect. So it's all reduced, it's all simplified. Let's go off to the side and quote unquote plug in infinity. Eight times infinity is, yeah, still infinity. Negative 1 over a really, 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 really big number. Yes, that approaches 0. Cross it out, write that this limit equals 0. What does that tell me about my end behavior? Perfect. Horizontal asymptote at y equals 0 on the right side. If you have not already, I'm going to give you guys an extra minute or two to go ahead and do the limit as x approaches negative infinity. And we already know that the radical 9x squared behaves like the absolute value of 3x. So you just have to decide if it continues to act like 3x or if it acts like negative 3x. So what does our radical 9x squared behave like? And why does it behave like negative 3x? Yep. Because x approaches negative infinity, which is negative. So I'll use my negative 3x there. My numerator would simplify into what? What would it simplify to? 5x. So we'd have 5x over 8x squared. Or 5 over 8x. Plug our negative infinity in off to the side. 8 times negative infinity is yep. And then 5 over a really, really, really big negative number. Guess how did I saw? What? And negative 0 versus 0, still 0. All right, so for my end behavior, same thing as last time, horizontal asymptote at y equals 0 on the left side. So I'm gonna end up repeating the instruction for the next part twice right now and then when we come back from our little break. Example 3. Oh, this is nothing like what you guys have on your paper. I need to redo that. I don't think I saved that. What you guys are gonna do is you need to decide if these functions behave like the absolute value function or if they just are like the normal function themselves when you reduce. Remember the entire reason that square root of x squared reduced to absolute value of x, because that x squared need everything positive. So it'll behave like that absolute value function. So I want you guys to, for this example, write down what you think it simplifies to, and then double check with the graphing calculator if it actually reduces to itself or if it'll reduce to the absolute value counterpart. You can do that when you get back from your break, and then I'll repeat the instructions again. So what do you guys think this reduces to, regardless of absolute value signs? Square root of x to the 4th. What would that reduce to, regardless of absolute value signs? X squared? Yeah. So I'm gonna graph the square root of x to the 4th. And I'm gonna graph x squared. If the graphs are the exact same, then I don't need that absolute value bar. I'm reducing it as is and everything would be okay. If part of the graph needs to be flipped, then I would use my absolute value bar. So let's take a look. They are the exact same graph. We do not need to do anything special for this. So even though this made the inside positive, it's kind of making it positive twice with that x squared squared. Everything's okay there. Is that okay? We'll do one more and then I'll kind of give you guys a little bit more time. What is this reduced to? Ooh, how did you get the x squared? No, that's okay. So we technically have a radical here. It has an equivalent exponential form. Alex. Yes, so technically you're dividing the index here in the power. All right, so let's go ahead and graph both of these. Square root of x to the 5th and then we'll do x to the 5/2. See if they're the same graph. If any side needs flipped, then we'll do the absolute value portion. Do we need the absolute value? Okay, so far we're not needing that absolute value. And that's okay. Not everything's gonna need the absolute value. I said before, if the inside makes it positive, then we might need it. But as we can see here, in example A, the output was already gonna be something that's always positive regardless, so we don't need the absolute value there. But if it reduces to something that would change the sign depending on whether you positive or negative values, that's gonna make a huge difference. Go ahead and try the rest of those and we'll take a look in a minute. When you have all of those done, I'd like to take a look. So I want to just write up C, D, E, and F without graphing yet. Just want to simplify them and then we can decide from there on out. What is the square root of x to the 6th? X to the 3rd. Cubic root of x. I want to talk about that after we get all those written down, but yes. What's this one become? E. Yep, x to the 2/3, and then F. So before we talk about the absolute value signs, remember at the very beginning, we talked about how the square root of a squared technically simplifies to a, but because the inside is squaring and making it positive, it technically behaves like the absolute value of a, making everything positive. This only happens when the inside is positive, where the inside power makes things positive. And the outside, or I guess the simplified version, can change signs. And what I mean by that is we have a regular A that could be a positive or a negative thing, right? And we make it just a plain positive by doing the absolute value. So let's look at this example. Look at all the insides. Which insides make our value positive? Out of all of them. A, C, and E. So these all kind of are meeting that first criteria for potentially needing that absolute value bar. The rest of them, we don't need the absolute value. We can even double check the graphs. They should be the exact same. So second thing, when we simplified the square root of x to the 4th, did that outside, we have x squared, right? Does that change signs depending on what kind of numbers I plug into it? Is it ever going to be negative? So we're not going to need the absolute value for that. This isn't going to change sign depending on what numbers I plug in. It's always positive regardless, right? Here, for part C, x cubed, when I plug numbers into that, is that going to potentially change signs depending on what kind of numbers I put in? So I'm going to need my absolute value bars to make sure that everything stays positive. Does that make sense? We can even double check the graph. Not that you guys want to, I'm sure, but. Yeah, so to make that left side of the red graph go up, we'll use the absolute value around it, and it should be hunky-dory. Let's look at the last one. When I plug a negative number into the x to the 2/3, is it going to come out negative or positive?
Positive.
Positive, yeah, because of the squared. So does this need the absolute value? No. because of the squared portion of it, everything should still stay positive. Do we have any questions? Honestly, for this reason alone, I was not really wanting to go over this in the last set of notes. I thought that this would be a lot to kind of do with the last one, so I hope you guys can appreciate doing it in a separate set of notes. Go ahead and flip it over to the next page and we'll do the last few examples. All right, so we're going to be using the limits at infinity of rational functions for all of these. I want you to write off to the side before you start evaluating the limits, how that leading term is going to behave. So for example, you guys can easily figure out the leading term of the numerator here. What is the leading term of my denominator? You guys are gonna make Audrey do it. Without thinking about it, it reduces to what? 4x squared. You have to decide, and you can even look back, decide if that needs the absolute value or not. If it does, go ahead and figure it out from there. If it doesn't, then just move into your next line using the leading terms only. So I'm going to give you guys some time to go ahead and work on that one. We'll go over it, work on B, work on the next one, blah, 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 blah. Miss Sandor, stop talking. Okay, so when we take the square root of 16x to the fourth, we get 4x squared. Does that need the absolute value? No, why not? What kind of values does 4x squared put out? All positive. So it's not going to change signs regardless of what kind of number we put in. So just leave it as 4x squared, even if you were doing x approaches negative infinity. Hint, hint, wink, wink for the next one. Leading term in the numerator. Perfect. We have our leading term for the denominator. What does that simplify to? And x over x squared. Where would the x go? Okay, so I'll just put that over x. Let's plug our infinity in. What happens when I divide by infinity? Yeah, that value approaches 0. Cross it out, equals 0. And that's literally all this question was asking. It didn't want to know what the end behavior was. It didn't want to know about horizontal asymptotes. You're just straight up evaluating that limit. And then looking at the next question, we already kind of discussed how 16x to the fourth reduces to 4x squared, which is never going to change signs regardless of the kind of x that we plug in. So it'll still behave like 4x squared. You guys can finish that one up and then move on to the back. I'll put the solution up here and then you can take a look when you're ready. Do not look at the board until you are ready to actually see the answer to part B. Part C, what's the leading term in the numerator? I want someone other than Audrey. She does a lot of sharing. Yes, what part of the numerator? Yes, x to the power of 3 over 2. Was that an even power on the inside?
No.
So it's not making everything positive. It is what it is. Leave it alone. Do not need an absolute value. Denominator. 10x. Okay, reduce that for me. What do we get? 1/10 x. Yep, 1/10 x to the 1/2. Let's try plugging infinity in. X to the 1/2 is technically what kind of root? Square root. So square root of infinity is still infinity. 1/10 times infinity. Okay. We okay with that? Last one. Leading term in the numerator. Ooh. Negative x. You said 2x to the power of 5/2 for the denominator? Yeah. So I'm gonna write square root of 4x to the 5th. Reduces to 2x to the 5/2. Did the inside make everything positive? No, so no absolute value. It is what it is. Reduce that, what do we get? We'll do the negative 1/2 part. My x is gonna end up being in the numerator or denominator. Okay. Technically has a power of 1 on it right now, but when I'm dividing the x's, what do I do with the powers? Subtract. So what is my new power gonna be? 1 minus 5/2 is what? Negative 3/2. Since it's in the denominator and I kind of made it so that it would end up being positive down there. We'll write it like that. Is that okay? Plug in the negative infinity. What kind of root is that? Cubic root or square root? Square root, yep. So we're taking the square root of negative infinity cubed. Negative infinity cubed is negative infinity. Square root of negative infinity doesn't exist. This is undefined. So what does that mean for our limit? Does not exist. Nice. Okay. How are we feeling? Somewhat okay? So biggest thing you need to remember to decide if you use that absolute value. I'm going to say it a lot. Does the inside power make everything positive? If it does, you might need absolute value. You might not. You just have to look at the second criteria. If it doesn't make everything positive, it is what it is. So if the inside power makes everything positive, you need to decide, does that simplified function need the absolute value? Does it change signs depending on what kind of x's I plug in? If it changes sign, you need that absolute value. If it doesn't, leave it alone. I gave you guys the practice that goes along with this before I check any of your answers. How could you check your answers? Plugging what into the calculator? Yes, plug the limit function. Well, plug the function that you're taking the limit of into your calculator. Look at the graph. See if it approaches the value that you think. I think there's one function on there that I can't remember which one, that it's not 100% convincing. So if you're unsure, if your answer doesn't match what you have on the graphing calculator, just have me take another look at it. And that is it. You guys can use the last few minutes to continue working on either practice 2.7 or 2.7 part 2.